All right. All right. All right. So today we're going to start talking a little bit about concentrations of solutions and specifically about molarity, which is kind of the most typical way that a concentration is measured. So first of all, we're just going to talk about what a concentrated solution means versus a dilute solution. So if we're talking about a concentrated solution, that means there's a large amount of solute dissolved in the solvent. So these are a lot of like Mio drops, or if you have a powder that you're making into something to drink, or orange juice, if you still buy it in the cans, frozen cans, and you have to dilute it. Any of those would be concentrated solutions. And then once we start adding some water, we end up with a dilute solution. So that one has a small amount of solute in it. And so we're just kind of looking at different ways that we can measure those amounts of solute. So we're going to talk a little bit about electrolyte versus non-electrolyte. And this portion of your notes we have actually already had before. Which this reminds me, there is a video for you to watch tonight, and please watch it because what we're doing tomorrow is a little bit hard, and so it'll kind of give you a little bit of a head start. So electrolytes are compounds that conduct an electrical current when they are in a water aqueous solution or when they are in the molten state, which just means they would be melted. So an example of this would be a salt water solution. And the reason something is an electrolyte and can conduct electricity is that there's a difference, but there's a positive, negative difference available for the electrons to move. So yesterday I said that if I have salt and we put it into some water, it doesn't just stay as salt crystals. It's actually going to ionize into sodium, positive sodium ions, and negative chloride ions. And so once that happens and there's that positive and negative difference, and that's when it's able to conduct an electrical current. So the things that form electrolytes are going to be, first of all, our stronger electrolytes. And those are when you have a large portion of the solute existing as ions. So for this one, I have my ions and my product would be greater than my compound that I started with. So things that will do that are aqueous solutions of ionic compounds. So that covers a lot. Strong acids. Acids that are considered strong are going to ionize almost 100%, and there's 6 of them. Sometimes you'll see 7 of them, but you need to memorize those. Remember, an acid starts with hydrogen, so any other acid besides those 6, those are considered weak acids. Strong bases will almost ionize almost 100%, and the strong base is a hydroxide with a group 1 or 2 metal, except beryllium or magnesium, the top of group 2. Those metals, they don't tend to ionize as much. Weak electrolyte means that the solution will still be able to conduct electricity, but just not as strongly because only a small portion of the solute exists as ions. So we see those with weak acids. So like I said, that would be any other acid besides what's listed. Also weak bases. And we mainly do the hydroxides, but ammonia is also a weak base that sometimes we come across. And then non-electrolytes are compounds that do not conduct electricity when they're in a water solution or when they're melted. So an example of this would be a sugar solution. Sugar will dissolve in water, but then it doesn't form any ions. So if you're talking about a non-electrolyte, then the compound that was the reactants going to be greater than the ions. And like I said, tomorrow we're going to do net ionic equations. So then that's whenever that really becomes, comes into play. So today we're going to talk about molarity, which is kind of the most common way that solutions are measured. So when we're talking about getting the concentration of a solution, we're looking at how much solute is in a given amount of solvent or a given amount of solution. And the most basic way that that is talked about is something that is called molarity. So that's the number of moles of solute in 1 liter of solution, and a capital M. This stands for molarity. So the formula is M equals moles of solute divided by liters of solution. And that denominator has to be in liters. So if you get your information milliliters, you got to move your decimal 3 places. So that's our formula that we're going to be working with today. And that's what your practice is over. So I'm going to kind of just show you a couple of different examples of different ways you might see it. Are we good? Can you not see? Liter of solution. I tend to do that for my solution. All right, any other questions on my very messy handwriting? I know, I'm not proud of it. It's just seems to have gotten worse as I get older too. All right, so the easiest one, I'm going to rewrite my formula right here. The very easiest one, there's not an most easy one example here, moles of solute per liter of solution. So the easiest one would be if you were given that, you know, I had so many moles of sodium chloride and I dissolved it in 100 liters. That's just going to be a fill in your formula. But of course, you got to do usually a little bit more work than that. So we're going to look at this one, calculate the molarity of a solution prepared by dissolving 11.85 grams of potassium permanganate in enough water to make 750 mils. So I'm going to go ahead and change that to 0.750 liters because I have to have it in liters. So if we look at our formula, there's nothing about grams, but we know that if I have grams and I know my compound, I can easily figure out how many moles that is. So we got to start there. I have 11.85 grams of potassium permanganate, but I really need it in moles. So I need to use my molar mass. And the molar mass is 158.04 grams per 1 mole. Remember, your units have to cancel out. So if I'm grams here, I need to have grams on the bottom on my next step. And at this point, we're at 4 sig figs because so far the only calculation we have used, or measurement, I'm sorry, that we have used is at 11.85. So you should get 0.0749. It's not a 9. 7498 moles of my solute. So now I have my denominator, so I'm going to divide it by my liters of solution, which is 0.750 liters. So at this point, when I get my answer, I'm going to have to go down to 3 sig figs because once I pulled in that 0.750, that's going to limit it to 3. So top top divided by the bottom and adjust for 3 sig figs, you should end up with 0.100 molar. I think on your calculator, I have this jotted down. So you must have gotten something like that, I guess. And then because I needed 3 sig figs, that would be this 9. And since there was 7 behind it, I had to round it up to 10 and that just continued. So that would be my answer right here. So I still have some people doing this step incorrectly. Remember, if you're given grams and you're needing to figure out moles, your number should be getting smaller because you're dividing by something. If you are given moles and you need to go to grams, then your number should be larger because you're multiplying by something, if that helps you out. All right, anybody have any questions on that particular one? All right, let's look at another one. We have, what is the mass of sodium chloride? So I'm trying to find grams of sodium chloride needed to prepare 175 mils. That becomes 0.175 liters. And I already have my molarity. So on this one, I'm not just filling in my formula. So I have my molarity. I have how many liters or partial liters. What I don't have is I don't have moles of solute. So that's what I'm going to have to solve for first. I'll solve for moles of solute, and then I'll use my molar mass, kind of reverse this to get to grams. So I'm going to say 0.500 molar. I'm just using this formula is equal to, we said 0.175 liters and X. I'm trying to find moles. So we got to do a little calc. No, not a little, some little algebra. I think that's algebra. Anyway, a little cross multiplication. So I end up needing to multiply 0.5 times 0.175. And when I do that, I get 0.0875 moles. And that is of sodium chloride because that is my solute. But we are not through yet because we didn't want moles. We wanted grams. So now I'm going to convert this to grams by using the molar mass. So if I'm going from moles to grams, should my number get larger or smaller? Larger because I'm multiplying. And the molar mass of sodium chloride is 58.44 grams. So 0.0875 times my 58.44 and limit it to 3 sig figs. Hopefully gave you 5.11 grams of sodium chloride. And if somebody's like me or another science teacher or somebody out in the real world is making a solution, obviously we got to have it in grams. You can't really measure out moles to make a solution with. All right, I want y'all to give the next one a try. It's a little bit different. And I'm going to give you the molar mass of sodium hydroxide because you eventually need it. So molar mass of sodium hydroxide is 40 grams per mole. All right, you'll need that at some point. So I'm going to give you a little bit. So I don't think anybody's gotten it yet in any of my classes. And I have confidence. All right, anybody got an answer for me? That is it. Perfect. 318. All right. Oh, yeah, Larry. You get, when you solve for your X, you end up with 0.318, but then because that particular question asked for milliliters, you had to move your decimal. All right, so let's work through this one. So my molarity is my 2.48 molar. Oops. And what else did I know? I'm trying to find my amount of solution. So now my X is on the bottom. And I need my moles of my solute. So I need to do that first. So 31.52 grams of sodium hydroxide. And we said it was 40 grams per 1 mole. So that gave me, what did that give me? 0.7880 moles. So that went over here. So we had to do a little bit more algebra. We're going to once again bring our X up. So we end up with 2.48X is equal to 0.7880. So when you divide by 2.48, I end up getting my X is equal to 0.318, and that's liters. And then, like I said, because this one particularly asked for milliliters, I would move my decimal and it would become 318 milliliters. So maybe a little bit harder algebra on that. Does anybody have any questions on that one? So those are kind of the typical problems you will see. Like I said, the easiest thing would be if you were given the moles of solute straight away, but usually you have to kind of work around that. All right, and then we're going to talk about concentration of ions in a solution, because we really start using this tomorrow when we're doing our net ionic problems. So if you have a strong electrolyte, we said it's going to ionize almost 100% in a water solution. So we'll use just this example, calcium chloride. That's an ionic compound. So if I put it in a water solution, it's going to ionize into calcium ion plus 2 chloride ions. And the reason there's 2 is because my little subscript of 2. So when you write a net ionic, not only does it need to be balanced with regard to elements. So for instance, I have 1 calcium on each side, 2 chlorines on each side, but also with regard to charge. So this compound is neutral. So I need my products to be neutral. And if you look, I have a +2, 2 times -1 also is a -2. So those 2 cancel out and I'm neutral on that side too. So I'm just going to make up a number. Let's say that I told you this was 0.50 molar. And if it's a strong acid, strong base, an ionic compound, then if I know the strength of those, I can also know the strength of my ion. So if this is 0.50 molar, my calcium is also 0.50 molar because it does not have a coefficient. My chloride, because it has this 2 times 0.50 is going to give me 1.0 molar. So if it's no coefficient, it's going to be exactly the same concentration. If it does have a coefficient, you're going to have to do that little multiplication. Notice you still have to worry about sig figs. I started with 2, so each of my other had to also be in 2. All right, let me do one more and then y'all can give another one a try. So I have calcium phosphide. So it's going to ionize into 3 calcium plus 2 phosphide ions. And once again, balanced in regard to element, also balanced in regard to charge. They both end up being neutral. So this is 0.25 molar. That's what's given to me. So my calcium is going to be 3 times 0.25 or 0.75 molar. And my phosphide is going to be 2 times 0.25 or 0.50 molar. Anybody have any questions on that? Pretty easy. All right, I want y'all to try the next one, and I'm gonna just give you some information. Silver has a +1, and sulfite is SO3, and it has a -2. So see if you can work through that one. You have to put together correctly for your compound, and then see if you can figure out the different concentrations. All righty. Oops. So this should have been your formula. Hopefully you got that part. And so when it ionizes, I end up with 2 silver cations. And remember, this SO3 is a polyatomic ion, so it's going to stay together, -2. All right, so I have done everything in regard to making sure that it's balanced with charge and also balanced within my elements. So if this is 0.33 molar, then my silver would be what? 0.66 molar. Didn't even need a calculator. And what would my SO3 be? It would be 0.33 molar. All right, not too bad. All righty, so y'all have a little bit of time to work on some of your practice. On this particular practice, if you look on the last page, all the answers are listed all together. I think on the last page is how I did that. Please watch your video tonight because I feel like it'll really help you get going tomorrow, kind of have a little head start.